This should be good.
Looks good.
Okay, so yeah, welcome to today's tutorials. As Ray said, I'm going to give a bit of an introduction into Kokkos before this afternoon you learn more about Sickle. The introduction I'm going to give today is really just a rather condensed tutorial. So there is significantly more material online to be found. We will probably do one exercise at the end if we don't have too many questions and delay in the, get too slow in the whole tutorial here. The exercises for this whole thing are available online also as like, later do alone if you want. There is the whole lecture series available online as well. I put the link also into the Slack channel. These whole lectures, they actually have also like walkthroughs for all the exercises. So if you later want to look at some of the stuff covered here and do the exercises as more of the exercises on your own, you can do that using the lectures. So what I want to introduce here today is, well, I'll tell you a bit about why one would want to use Kokkos, why we need it, and then I'll give you an introduction into some of the core concepts of Kokkos to just give you an idea of how programming with Kokkos looks like, how it generally works, and what the look and feel for codes is. So first, let's talk a bit about why we actually have this project. So if you look at the current generation of machines, right, the stuff we have online right now, and maybe I should have updated the slide since NERSC Perlmutter actually is now online. But if you look at the current machines, right, we have like Trinity, we have Sierra, we have Summit, we have Astra and Fugaku. And if you look at what the kind of primary programming models are people are suggesting to use there, the vendors, it's OpenMP for the CPU machines, and it's basically CUDA for the GPU machines. Now there is also, or there was OpenMP available on Sierra and Summit, or was supposed to be, but the compilers have been so bad over time that it didn't get too much use on the current machines. The OpenMP compilers are getting better now in particular the OpenMP offload compilers. And I guess you heard a bit about that yesterday. So at this point, it's at least a viable option, but they didn't used to be on the current machines. Now, the upcoming generation looks actually a bit more complicated because we still have CPU machines flying around, or we're gonna have CPU machines flying around. For example, Fugaku is obviously still, going to be active for quite a while, but also an upcoming Crossroads machine that's at Lenel will be CPUs only. But all the other machines are GPU machines. In contrast to current generations, it's different GPUs on different machines. So we have still Perlmutter, which just came online with NVIDIA GPUs. So that shouldn't be a change from today. But then we got Frontier and Aurora upcoming, as well as El Capitan, and these machines use AMD and Intel GPUs. And the problem with that from current generation codes is perspectives is that the primary recommended programming models on these machines seem to be HIP and DPC++, or Sickle DPC++, which you're going to learn about later today. Now, why is that a problem? The problem is that you have to rewrite your code potentially. If you had a CUDA code before, then that's not officially supported on any of these machines, and you have to rewrite that. And if you think about how much it takes to rewrite a code, that's a bit of an effort. There's this industry estimate which says that full-time software engineer, somebody who works at Google and Microsoft or whatever, to just write code, can write like 10 lines of production quality code per hour. So about, you can get 20,000 lines of a person out, in a year. And if you look at typical HPC applications, some of these, bigger known codes, we have around, 300,000 to 600,000 lines. Just at Sandia, we maintain a few dozen of those. And then you have these large scientific libraries, things like E3SM and Trillinos, which are millions of lines of code. And in a conservative estimate, you need to touch about 10% of your code if you switch from stuff like CUDA to Sigil. And that means it needs multiple person years per app to just rewrite that. And usually, as a academic or somebody at lab, you don't really have that kind of time. You have other things to do, like writing proposals, writing papers, doing actual science, right? Not just rewriting your code, constantly, because you get a new type of machine every few years. So Kokkos is essentially our answer to that. Originally it started as something which is just the C++ programming model for performance portability. It's effectively implemented as a template library on top of things like CUDA, HIP, OpenMP, etc. That means, it's technically you have native CUDA and HIP code underneath, right? And there's no like extra compiler involved or something. You just use the primary tool chains on each platform. And it's just abstracted out, as a C++ library. One of the aims of a programming model, and that's a bit of a difference to some of the other programming models, is that it's supposed to be very descriptive and not prescriptive. Which means that basically you describe what you are doing, in algorithmic terms, and Kokkos is responsible for mapping that to the underlying architecture. That means you don't have quite as much control as in a lot of the other programming models. But on the other hand, it prevents you from writing yourself into a corner and writing code which isn't portable to other platforms. We also try to align with the development in the C++ standard. And I saw the question. I'm gonna come to that in a minute. So we are trying to align with the developments in the C++ standard. Actually, it's kind of funny, at the last in-person meeting, Kokkos developers, from various labs, as people who work on Kokkos itself, on the core library, were actually the third strongest contingent at the C++ committee after Microsoft and Facebook, I believe. So the thing is that a programming model itself is not enough, right? You need a bit more when you actually want to write big applications. You need math libraries, you need tools, etc. You need to be able to integrate, with Fortran and Python and stuff like that. And so the Kokkos ecosystem is what is, attacking that. And there's a number of interlocking projects which essentially provide these kind of capabilities. We have, a project which provides these math libraries. We have projects which work on a dedicated tools, infrastructure, etc. And the whole thing is developed as open source. So we are a growing community. You can find us on GitHub, and we have literally hundreds of users at many large institutions. My current estimate is that we have on the order of 200 projects or so using Kokkos. And so the whole idea is, you write your code towards Kokkos, and then Kokkos maps everything to the underlying stuff. I mentioned it already. We have this Kokkos ecosystem, and we have this Kokkos core, which is what I'm going to talk today about. Where we have the which provides for parallel execution and parallel data structures, etc. And then there's Kokkos kernels, the math library, which provides linear algebra kernels, graph kernels, etc., as well as the interface to vendor libraries, like MKL and Kublaus and Kusbars and stuff like that. There's the Kokkos support, which is actually funded through ECP, which gives you these kind of tutorials and development of material, etc., as well as running boot camps and optimization camps and stuff like that. And then there's the Kokkos tools effort, which does debugging and profiling and tuning. One question somebody had is, where does the Kokkos name come from? So if you're familiar with Trillinos, right? Trillinos is very fond of its, Greekish names, and Kokkos actually is Greek, and it essentially means something like grain, or like like a grain of sand or a corn grain or something. And essentially where this came from is that originally Kokkos was intended just for this kind of linear algebra stuff, and essentially it was the kind of grains with which you build your solvers, right? That's where the name is coming from. The benefit of all these things is that things like Kokkos, the name, are rather unique, and you actually find, if you Google Kokkos, you actually find just pages upon pages of stuff which actually concerns us. Currently, Kokkos is maintained by a group of labs. Sandia was where it originally started, but now Los Alamos, Argonne, Oak Ridge, and Berkeley have developers who contribute to Kokkos on a basically daily basis, as well as CSCS, which maintains the HPX backend. And there's a huge group of people involved. Regarding the ISO C++ standard, right? One of the goals what we have there is what we are proposing kind of new features for the C++ standard. And the idea here is that we get some of the core concepts and some of the core difficulties into the C++ standard, so that long term, it's not just our job to maintain these kind of capabilities. What we then do, and we're actually actively doing that right now, is we backport accepted capabilities to like current compilers, and we essentially make the Kokkos API, which usually is going to be a bit different than what actually got accepted in the C++ standard then later, just a thin wrapper around that. We are doing that, for example, with our main data structure right now, which is the Kokkos view I'm going to talk about a bit later, and that is now going to be replaced by MDSpan. So one thing, there was a question, is there any guaranteed long-term funding for support and development in Kokkos? So that is a question we are getting a lot. And obviously I can't tell you that there is guaranteed funding forever for this, right? But there is no guaranteed funding for Clang either, right? Nobody said, promised, and gave you an ironclad guarantee that we're going to fund this thing for the next 50 years. That said, at Sandia itself, right, we have essentially committed our entire code base to this, as more or less everything, or let's say 90% or so of what we do on GPUs or on current machines is based on Kokkos, and that includes our nuclear weapons codes. And ASC is a program which has essentially continuous, which funds this, is a continuous funding project. It's not something which is like, kind of time limited. And that means, that stuff needs to fund this for, rather longish time, because, all our codes depend on it. And we literally invested hundreds of person years in porting codes to Kokkos. So, it's quite an investment. And then there is a lot of other like applications, at other labs, at a university, etc., which use this. Think about ECP, right? The exascale computing project. Kokkos has in the exascale computing project, I think 18 critical dependencies. So 18 other projects depend critically on Kokkos. As a comparison, I think there's 21 which critically depend on Fortran and 20 which depend on C instead of C++, right? There's like 56 or so which depend, or 59 which depend on C++. So within ECP, right, you can argue that Kokkos at this point for DOE, is almost as important as Fortran, right? And so do you think, they completely stop funding for Fortran compilers? Maybe at some point, but probably not likely soon. So I hope that answers the question. Okay, any more questions on this? If not, we're gonna get into tutorials in a second. But before that, let's talk a bit about online resources. So as I said, there's a primary GitHub organization, where is the slides and recording and so on for lectures. There's the wiki, which includes like API reference for Kokkos, etc. And then one of the most important tools we have is the Kokkos team Slack. That's the Slack channel for Kokkos, and we have, I think of today, we have like 660 or so people in the general channel, and including the entire Kokkos team. And so you usually get answers there rather, rapidly. I can whitelist domains. I have, most of the DOE labs are whitelisted. I have a lot of universities, etc., whitelisted, but I can also invite individual people. So if you want to join, that's good. Again, so there was another question. There's a lot of proposed frameworks, Roger, Kokkos, etc. What push to allocate you much effort in yet another framework? So first of all, in some sense, Kokkos is not yet another framework because it's kind of original framework, right? Kokkos predates things like Roger and Alpaca and what's the other thing, Orca, etc. At the time, I think it wasn't clear what the right solution is, and a lot of other people started something. At this point, is there a reason to maintain all of them? Yeah, maybe. We'll see. But I think I'm not wrong to say that Kokkos is probably the most widely adopted of these ones. And compared to, I think that's just a fact that Kokkos has probably more users at this, quite a bit more users than any of the other frameworks at this point. Okay, let's talk about data parallel patterns. So what I want to teach you in this section is how you essentially express parallel code in Kokkos, how that is mapped to execution resources, and what the difference is between a parallel for and a parallel reduce. And when we there's an exercise associated with that. I think we'll push that to the end so that we can do that as like one block with another exercise. So in Kokkos, if you think about your typical loop, right? What you have there is what we call, and we go in that in more detail in the lengthier lecture. We have a pattern, right? And the pattern you have here is like that of a for loop, right? You do something for a range of indices. You also tell the loop, from where to go, right? What is the range of indices you're going over? And when you have something you do for every iteration, right? For every index, you do something, and that's what we call the loop body, right? So in Kokkos, that is our unit of work, right? Each iteration of a computational body is a unit of work. So we're not. And you don't have to technically think about chunks or anything like that. You think about individual iterations. The iteration index here is the identifier for a particular unit of work, and the iteration range essentially identifies the total amount of work. And what you are going to do in Kokkos, right, is you essentially give us an iteration range in the computational body, and you hand that to like a computational pattern, and then Kokkos decides how to map that work to execution resources underneath. So how do you give that computational body to Kokkos, right? And basically you do that like in every other C++ framework, as including the C++ standard library, essentially as functors or function objects, right? Which is a really common pattern in C++. I mean, you do that when you use like standard algorithms for each or transform, reduce, etc. It's also the same what you would do for like Circle, for example. So what is a functor, right? A functor is essentially a function with associated data. And the idea is that allows you to pass around a function, in self-contained thing which can execute work. And technically, syntactically, what that is it's a struct which has an parentheses operator, so a callable operator, right? So what you now do in Kokkos, and I'm going to come back to that in a second in more detail. What you do is you give, for example, to a parallel 4, just a parallel 4 loop. You don't hand at Kokkos the number of iterations, and you hand that functor, and then Kokkos decides how to execute that. Now I said the identifier for a Kokkos unit of work is the index, right? So that means in the normal, simple base case, your operator of your functor essentially just needs to accept that kind of index, right? So it gets the loop index. Now, one word of warning here is that that concurrency and ordering of parallel iterations, right, is not guaranteed by the Kokkos runtime. So that means we don't tell you, that iteration 0 gets started before iteration 1 gets started, right? We don't guarantee you, that we don't randomly shuffle in which order we execute these things, right? We also don't guarantee you how many of these guys are active at the same time. So by not guaranteeing you any of that, basically it allows us to do all kinds of parallelism schemes for this, right? If we don't guarantee you either of these things, it actually means that your loops have to be vectorizable. It means that your loops are pipelinable. It means that I can thread them. It means I can have them execute them on the GPU, etc. So how does that now complete look? If you actually also have the data in there with a functor. So you create that functor, you figure out in that operator, you copy essentially your loop body. And then you figure out what is all the data elements, all the data structures or whatever I access. And you make these guys members of a functor, data members. You write a constructor which initializes these guys, and then you can call parallel 4, you give it the number of iterations and that functor. Now, obviously that is rather, tedious to do that for, I don't know, the 10,000 loops we have in one of our big codes. And there's a better option for that. And that was introduced in C++11. So, it's been a while. And actually, technically, Kokkos doesn't support C++11 or the latest version anymore. We require C++14. But, the concept stands. And that's lambdas. So lambdas are a way to auto-generate these kind of functors. And they're really not magic, right? What happens here is that you define the operator, right? This is this, if you look at this const blah, blah, blah here, that's essentially the signature of your operator. You add the loop body as if you had defined, a member function here. And then you add something up front here, which essentially tells it how to capture members it finds here. So the compiler will go through your loop body and see all the things you reference. And then it will essentially create copies of these guys as members in the auto-generated struct. And this thing here tells it how to generate them. The equal sign means construct them by copy constructing. There's an ampersand version which says just take a reference to these things. And in Kokkos, you actually have to use copy by value or capture by value. And the reason is that we might need to copy this thing to the GPU, right? And the GPU might not be able to access references captured on the host. Remember, this is still executing on the host, right? This is just your normal code, right? That's where the capture actually happens. Now, capturing by value has a couple of side effects. One problem with that is that data structures which are containers or have container semantics like std vector are a bit problematic, right? Because if you capture a std vector, it actually by value, it actually creates a new allocation, copies all the values over, and now you have a new copy, right? If atom forces here were a std vector, right? All the updates you do here are lost by the time the parallel 4 is done, because the lambda will be destructed, and which means that the copy of that std vector you created, which was updated, also get destructed, and your original copy doesn't know anything about it, right? This is completely independent of any other std vector you might have had here. So what we need is data structures with reference semantics, like pointers, right? Or later Kokkos view. Now, one problem, I mean, one reason why that isn't maybe as much of a problem as you might think is that std vector anyway doesn't compile on the GPU. So, you know, it's not an actually additional problem, but it's something to keep in mind. So how does this compare then to like just OpenMP? We have the serial version of the loop, right? You have just your normal for loop, and in OpenMP, what you did yesterday, right? You write something like pragma OMP parallel 4 on top of it, and in Kokkos you just write parallel 4, and then you know, add that little bit of lambda syntax. So all in all, right, this is actually a bit less typing than in OpenMP, but it's, you know, really not more conceptually difficult than, you know, OpenMP or even serial stuff. It's just that the annotations in Kokkos go in a slightly different place than where we are in OpenMP. Okay. So one thing, there's a question, how does Kokkos handle cases like, you know, things like std vector or other stupid things? You know, how do you get like nice compile time errors, right? Now, we are trying our best there, and we actually invested quite a lot of work into, you know, getting reasonable compile time error messages. Generally, obviously, but reasonable is, you know, depends on your reasoning, right? Generally, in template code, right, what you do is you only ever go to the very first error you get. Don't go to the last one, because one error at the top, you know, essentially just causes hundreds of subsequent errors potentially. But one thing we are doing is, which makes it a bit easier for you to find that you did something stupid, in particular this kind of container semantics, is that we actually make our lambda const or functor const. So your operator in a functor needs to be actually marked const. And that means assignment to something with container semantics will actually not compile via a message which just says to you, you know, this thing is const and you can't do that, right? So at least you won't get like a silent error if you know, even if you had like a different container which actually compiles on the GPU, you wouldn't get silent errors that, you know, you silently lose your results, right? The Kokkos would, as this thing would just not compile. Okay. You probably get a weird error if you have std vector on the right-hand side, and there isn't really much we can do about it. You know, we could try writing a compiler, but that's outside of our scope. Okay, let's talk about some a slightly other thing here, and that's you know, what happens if you want to actually do like reductions, right? Integrations, for example. One simple example is this kind of Riemann sum style integration, right? And you have this, you know, this simple loop, right? In serial, you have this total integral up here. You know, you do your loop, you update the, you know, you compute your contributions for each iteration, and then you sum it up into the total integral. And how do we parallelize that correctly, right? I mean, we saw there's a for, you know, there's a range call, and there's a loop body. Didn't we see that just now, right? So let's just use a parallel 4. And, you know, if you do that, you get this compile time error I just mentioned, right? You can't sum into total integral because total integral is const. And that's because this thing captures by lambda, and we treat this as const. Now, if you're a C++ programmer, right, and you know your C++, you say, you know what, I know how to work around this. I can just get myself a pointer to total integral. I capture the pointer, and then I update that pointer, right? And yeah, that actually compiles. But what happens is you're getting a race condition, right? you know, a plus equal is essentially a load of the destination when, you know, the sum in registers and then a store. Now, if you have one thread loading this guy and while it's incrementing, have another thread loading this guy, you know, they actually loaded the same value. So the first one then writes its thing back, the second one does the increment, you know, and then writes its result back, and you lost the contribution from thread 0. That's, you know, the typical race condition. Now, now the root cause of what's going on here is that you used the wrong pattern. Your computational pattern here is not a for loop. A for loop is something where every iteration is essentially independent. What you have here is you have a reduction, and a reduction pattern is when you know the iterations all contribute to kind of the same thing, right? The same value. This is different from scatter patterns. There are other patterns, you know, which are or computational, you know, algorithms, scatter algorithms, which are some, you know, in some sense a reduction, but it's not the reduction in this sense here because they don't contribute all to the same value, right? Reductions are when everybody contributes to the same value. So how would you do that in OpenMP? In OpenMP, you know, which you saw yesterday, you add that reduction clause to your pattern, and you tell it, you know, what kind of reduction it is and whom you reduce into. And in Kokkos, we're going to do that roughly the same way. We tell it now we use a reduction pattern, a parallel reduce, instead of a parallel for. We still give it a range and a functor, and we give it, you know, a place where to store the final result. Now, if you look at that in this kind of scalar integration, one thing which changes on top of what I just said, you know, that you use a parallel reduce is you add your operator for your lambda has now a second argument. And what that second argument is essentially the value you update by your item of work. And what that second value really is, the second argument really is a thread private value. And that thread private value is essentially managed by Kokkos. It's not the final reduced value. It's just where every thread puts its contribution and then combines it at the end. In fact, OpenMP does exactly the same thing. If you were to print out like the address of total integral in this loop, what you will find is that every thread has a unique address. And potentially none of these actually are the address up here. The compiler internally does that for you. It replaces your global total integral with thread local variables and uses these thread local variables in here. And then at the end, the OpenMP runtime combines them all and puts them back into total integral. And the plus here actually only applies to the combination. You could write here times equal and get, you know, some rather weird type of integration. The same is true for Kokkos. You have to do the type of reduction you want, you know, for the global reduction as well here explicitly in the work item. So I think I'll come to that a little bit later, to that question. There was a question in the chat. We spent some time yesterday discussing OpenMP block allocations of parallel 4 and the pitfalls of false sharing. Does Kokkos have safeguards to watch for problems like this, specifically when we're writing something like an in-place array update and blah, blah, blah. So basically, by default, we do the right thing, and we come to that later when we talk about views. But effectively, we are doing scheduling to platforms so that if you write, you know, just typical loops, right, and you parallelize over, you know, your loop iteration, that you minimize false sharing, even in like dynamic scheduling, that you get proper coalesced memory access on GPUs, right? Because on GPUs, it's actually the other way around, right? It's not about false sharing, but you actually effectively want sharing all the time. And we'll come in detail to that later when we talk about memory layouts and memory access patterns. Hope that answers the question. Okay, So one other thing I want to tell you is, remind you is, you should give your kernels names. Kokkos actually in its interface allows you to provide a label as a first argument to these parallel patterns. And this label essentially is anything convertible to a std string. Typically, I would recommend actually providing like, literal string that cuts off something like, I don't know, 100 nanoseconds or 200 nanoseconds in the launch, or 200 cycles or so in the launch, launch command, because it doesn't have to do like, it doesn't necessarily need to generate an allocated string, largely because the compiler then can figure out that this thing is const, and it potentially isn't used later. What these labels do is they are essentially used by our profiling and debugging infrastructure. And there's a whole profiling tutorial on this. But one of the things which is really neat about it is that essentially what's going on here is that Kokkos has a built-in instrumentation layer. And that instrumentation layer is essentially similar to what you have in NVTPX and is that what it's called? Yeah, I think so. And the ITT from Intel, etc. But it's already built into this thing. And the way that instrumentation layer works is that the instrumentation layer actually is activated if you load a tool at runtime. So you can set an environment variable, point to a profiling tool, and that thing then will be loaded. And if no tool is loaded, essentially the cost of that instrumentation layer is just something like a function pointer comparison, whether a function pointer as the callback is set or not. The neat thing is that a number of common big tools also now support the Kokkos instrumentation layer. So things like Tau, for example, or HPC Toolkit are actually having built-in support for the Kokkos instrumentation layer. So if you name your things, you actually have these names show up in your profiles instead of some random, a type ID, which is rather complicated considering the abstraction layers in there. And so naming your stuff is really useful. We do not require you to provide unique strings, so you don't need to be completely paranoid about, there's nobody else I'm linking to name their kernels exactly the same way. But profiling tools would, tend to mesh these things together, right, if they have the same name. But believe me, it's absolutely super useful to just give every one of your parallel patterns a nice name. The exercise, which we'll try to do then later in the second, probably in the last quarter of our tutorial time, so after the break, will basically be this, right? We're gonna have this kind of inner kind of product thing. You have a matrix, a dense matrix, which is not necessarily rectangular, it's or not square, it's rectangular. You have two vectors, and what you do is you multiply these guys together and multiply with this guy together, and you get kind of one single result. So we'll come to that back later a bit more, but let me talk about that right now. One thing you have to do in Kokkos is you have to initialize and finalize Kokkos, and that initialization and finalization is exactly like equivalent to what you do in MPI, right? So essentially what you would do is you would just after you initialize the MPI, you would call Kokkos initialize. That is what also the vendors used to recommend, but there is a couple of, depending on your MPI, there's a few variants where you have to initialize Kokkos before. The reason that we actually recommended doing it after is because MPI initialize is potentially allowed to do the process binding of your process. And Kokkos initialize should honor that, and use that information. Now, there's otherwise, on the other hand, there's a problem that some MPI things want you to set the GPU ID before you call initialize. And so Kokkos initialize would be responsible for setting the GPU ID. And so in those cases, it might be useful to call it before. Unfortunately, I don't have a super good guidance on that. And you have to finalize everything. One thing we do in finalizes, we check for memory leaks. So all our Kokkos data structures need to be deallocated before you call finalize. Otherwise, you're gonna get complaints. One more thing about this is, at present, you cannot call Kokkos initialize again after finalize, which actually is equivalent to MPI. You're not actually allowed in the standard to call MPI initialize after you called MPI finalize. So in Kokkos, it's the same thing. Largely, this has to do with some of the lazy initialization stuff and optimizations we do on a per kernel basis, which essentially has also lazy kind of configuration stuff on a per kernel basis, and resetting that properly is and keeping track of that properly is rather difficult and actually would involve some overheads we rather not have. Okay, we're going to come back to that a bit later. Basically, this first exercise, because we haven't managed data yet, will only run on the CPU. So we can run that with OpenMP and stuff like that. Generally, the exercises, they have like 3 arguments, or we have a couple of arguments. The capital S essentially provides the total size, effectively the total number of elements in the matrix, but as a power of 2. So, if you have like S26, then there is 2 to the 26 elements in this thing. And you can change the number of rows by specifying n in the same manner. Okay. I'm not going to go into that. We're going to go into that later. So what I hope you saw from this is that if you just do like simple loops and stuff like that, it's kind of similar to OpenMP, right? It all kind of just works. There's 3 common data parallel patterns. We talked about parallel for and parallel reduce. We didn't talk about parallel scan. So parallel scan is another thing which does like a prefix scan pattern. And you parallelize your computation is essentially characterized by this pattern, with parallel for, parallel reduce. The policy, which in this case, so far we have only given as a policy like range, and the loop body. And you provide these computational bodies as functors or lambdas, which handle a single work item. Any more? Any more questions? There was a question regarding are things like block sizes, etc. Easily adjustable. The answer is largely not, or depends on the thing, right? There are certain patterns or certain execution policies where you can, where are others where you can't. But what we do have is we have an auto-tuning framework, which also allows you to write your own auto-tuning tools, which can do a lot of this thing. What we found in our big applications is that over time, people optimized, block sizes for something, and then they lived with these choices for 10 years, even though it only gave them, benefits on the first 2 of the time. So generally, we are trying to avoid that and set that for you. The make error you have here is you just need to set Kokkos path in the make file of the exercise correctly to wherever you have git cloned Kokkos. Okay. Is there any other question? If not, I'll go to views now, introducing some data structures. Okay. So what I want to talk to you now about is, we'll talk about what we call our view abstraction. So and what, talk about the key concepts for view, its template parameters and its life cycle. So think about, you actually want to do something with data, like you want to run like a DEXB, on the GPU. And you started with just like some, kind of CPU code, right? And you wrote this Perl 4, and you had before that, you created like some pointers, right, for X and Y and whatnot. Maybe you wrote your functor where you capture, have these members all explicitly. Now, there's a bit of a problem, right? If you allocated just something with new, that memory resides on the CPU and isn't necessarily, accessible on the GPU. And basically what we want is we want the way of storing data. And with data, I mean, in this case, as a fundamental building block, multidimensional arrays. And I want to have a data structure which can be communicated to an accelerator. I want a data structure we can reason about, where's the data accessible? How do I copy something over, etc. And that data structure in Kokkos is View. It's a pretty lightweight C++ class, even though its implementation is rather complicated. Basically, what it contains is a pointer to an array and a bit of metadata, stuff like its length. It is templated on the data type and some other things. So the high-level example here would be, you create these views, and then you just capture them and you use them. Now, you see that I can just capture them by value, and the reason that I can do that is that views have reference semantics. That's why they are called views. So they essentially work like pointers. And that means you can copy them into your functors. And that also means that you don't have to pass them along by reference, in most cases. So what is a view? A view is a multidimensional array. And that multidimensional array can be, of 0 or up to 8 dimensions. So 0 would be like just a scalar. 1-dimensional would be vector, 2-dimensional matrix, etc. The number of dimensions, it's what we call its rank, is fixed at compile time. These arrays are rectangular, we are not ragged. So that means, for example, in the matrix, every row has the same length. And you can set dimensions at compile time or runtime. And you access elements via its parenthesis operator. Here's an example for 3 variants or 4 variants of a 3-dimensional array. The first one, double star star star, right, is an array with 3 runtime dimensions, which we stars denote. And so the constructor, it takes a label, again, for profiling purposes and debugging purposes, and then 3 runtime parameters. The second one has 2 runtime dimensions and 1 compile time dimension, and then the last one has 3 compile time dimensions. And if you have 3 compile time dimensions, you don't give any runtime lengths to the constructor. Note the stars here do not imply that we have pointer chasing going on. The underlying data structure is not a pointer to pointer to pointer. The underlying data structure is a 1D array. The stars here are only denoting runtime dimensions. So we essentially just use that in some like type deconstruction to figure out what rank is. Because in C++ you can't write doubles, n2 star n2. It's not actually a legal type. Runtime dimensions have to come first. We're probably gonna give you an option in Kokkos 4.0 next year, which doesn't do that because which has a different way of defining ranks, etc. Which is the way the MD-span proposal for the C++ standard does it. And when you access it, like in Fortran, you just write IJK. Okay. I see there's some problems. There's really machines which don't have BC. Oh my goodness. I can tell you later how to fix that, and we can potentially build with this. I'll talk later a bit about how to build with CMake as well, as an example. And then we can do it. So another thing to know about views is generally we are not trying to do any. We are trying to avoid allocations, in places where you don't necessarily expect them. So the primary allocation mechanism is when you call the allocating constructor, and the allocating constructor is the one which takes a label, right, for all intents and purposes. If you do copy construction or assignment or whatever, there's never an allocation happening. Copy construction and assignment are shallow, like pointers. And one thing about this is that we actually do reference counting. So, which means that, if the last copy of something goes out of scope, you get automatic deallocation. Effectively, views behave like shared pointers for most of the time. So what does that mean? If you look at this little code, right? I'm creating a two-dimensional array with like one runtime and one compile time dimension. I create two of these guys, right? Then I assign B to A. Then I copy construct B into C. And now I assign, to A02, B02, and C02, 1, 2, and 3 in sequence. What gets printed here? Any suggestions? Anybody wants to hazard a guess? The answer is 3. Right? So what happens here is, in that first line, I'm getting two allocations of n by 5 and k by 5 length. But now in the second line, I'm assigning B to A, which means that A's allocations reference count is reduced to 0, so it gets deallocated. And A is now pointing to the same allocation as B. In fact, if you were to ask A what its label is, it will tell you B. The reason is that the labels are associated with the allocations, not with like the object itself, right? It also means that A's length is going to be K now. Now you copy construct into C. And one thing you see here is that it also converts, C is going to have two runtime dimensions, just that its second runtime dimension, type-wise is 5, right? And now I'm assigning to stuff 1, 2, and 3. Because these guys are all aliasing each other, right? This all points to the exact same memory value. And that means, the last, they overwrite each other. And so the last one gets printed. There's a question of how you copy actual underlying data, and we'll come to that in just a minute. Okay. So there's a number of view properties. One of the most important ones is the extent, which is essentially just how long is it in each dimension. There's also a static extent function, and static extent can be used in like compile time context, right? Stuff like template parameters, right? I think it returns, oh my goodness. I think our documentation tells you what it returns if you try to do that for a runtime dimension. It returns something. You can retrieve its raw pointer, the underlying pointer via its data function. And you can get its label, asking via the label. So if you allocate this thing, right, you can you see that A with a runtime and a compile time dimension, its extent 0 will be n0, its extent 1 will be 5, its static extent 1 will also be 5, right? You can ask that its data is not the null pointer. It's not in this case, right, because you allocated something, and you can ask for its label. two views and destination comma source, and that can copy between things. Okay, now in all of what I told you so far, right, I didn't tell you anything about how to control where stuff executes, right? Also, does it run on the GPU? Does it run on the CPU, right, etc. And that's what execution spaces are for in Kokkos. An execution space is essentially a homogeneous set of cores and some execution mechanism, right? It's something, a place to run code, right? A way to run code. So in Kokkos, where execution spaces, serial, threads, OpenMP, CUDA, HIP, etc. And these are all different mechanisms. There was another question: how can views be used with MPI? I presume you can just pass a view to an MPI call for like doing 2 of the exercises, which should get everybody to actually compile something and actually run it on the GPU as well. Okay.
Okay.
I just thought that we'll do it as one block at the end instead of interrupting in this kind of short time here, because every interruption adds a couple of extra minutes. Okay. Sorry for that takeout. Did you actually hear my MPI answer?
No, we didn't.
Okay. So you can't pass the MPI to MPI the Kokkos object itself, right? Because obviously it only takes raw pointers and sizes. But there is you can just use that data function, and then there is a function called Nevin, help me out. Is it just span or is it?
Yeah, I think so.
Yeah, I think it's just span. Yeah, span, which essentially is the product of the extents, is in simplification, but it also includes like potential padding or other things, depending on what's going on. You only have to be careful with that when you do subviews, because if it's not a contiguous subview, right, the span thing will include all the other parts of the original view, right? But basically, you just pass .data and span to it in the simplest case to MPI, and then that just works. And on most of the modern platforms, right, you can directly pass also like GPU allocations there, so it doesn't really matter where the view is, because MPI can handle that. Okay. So did you guys still hear what I said about this slide, about the execution space slide, or was I already out?
A little bit. I think you break in the middle or something like that.
Yeah, okay. So basically I was talking about how, execution spaces is how you control in Kokkos where something runs. And these execution spaces are with, some place to run code, right? So they are associated with some kind of hardware resource underneath, but we're also the execution mechanism. So for example, on the CPUs, right, there's actually serial, there's threads, there's OpenMP, there's HPX, which are all execution mechanisms on CPUs, right? And if you have an execution space instance of that created, it is associated with that plus a set of like hardware resources. Other ones are things like CUDA and HIP, etc. In principle, Kokkos can.
Oh no, you are breaking again. We cannot hear you. Are you still here?
Okay.
Okay. So essentially the execution spaces, as what we had so far, right, we gave a policy, right? And that policy was just an integer. And what you can do is you can explicitly give a range policy, and that range policy has a template parameter which tells it where to execute, right? And that's the execution space. So that means you can choose for a kernel, where it goes, whether it goes on to the CPU or the GPU or wherever. and you just provide, you know, a begin and an end. This range policy also allows you that begin and end, right? While if you just give an integer, it implicitly means starting at 0. In fact, that integer actually is just getting forwarded to range policy with no template argument, and then 0 and the number of intervals or number of iterations. That is a thing which is a common theme throughout Kokkos, that a lot of our things are defaulted, and so by default we do the, you know, most common thing kind of, you know, that's what's happening here. Okay, can you click one down?
Do you want another slide? Is this okay? Next slide.
Wonder if we lost me. Do you have the phone numbers for Zoom? Like the meeting invite doesn't have them.
Let me see. I think
To
you have.
figure out what
So where were we? So basically what I said is that, you know, you have to have these things compiled in, right? And then you also need to mark up your functions and lambdas with a macro. The current code where you see here actually doesn't have that. Can we go to the next slide? So what you need to do is you essentially need to annotate every function you want to call on inside a parallel 4 with some macros. And the main macro is Kokkos inline function. What Kokkos inline function does is it essentially just does whatever the backend you know, compiler needs in terms of markup. It does that kind of markup. So for CUDA, for example, it would imply inline device host, right? Which means that your function is callable on the host and the device, because, you know, you can choose the execution space where to execute something, right? So the same functor could be given to you know, something which where you use a range policy with CUDA as the execution space, as well as range policy of OpenMP. Can you click one further? Now, the same as for lambda, the lambda annotation needs to be slightly different, and it actually includes what we do there is it includes the capture clause. There's also some other annotations. There's, for example, Kokkos function, which doesn't include the inline, because we actually do support things like relocatable device code, etc. There's also a special macro for defaulted functions, because unfortunately, depending on your CUDA version, you know, whether or not you are supposed to mark up defaulted functions changes, which is rather interesting. It also depends on the compiler. I think Clang and NVCC don't quite agree on whether you need the markup or even are allowed to do the markup. Okay. So memory spaces. The other thing is we had now the execution spaces, right? We also have memory spaces, and essentially memory spaces are, you know, some kind of explicitly manageable memory resource, right? It's a place to put data. And again, as with execution spaces, Kokkos doesn't just have like device and host memory. It in principle can have arbitrary number of memory spaces. On top of it, there isn't a one-to-one correspondence between execution spaces and memory spaces, right? There is rather a mapping, right? Which execution space can access which memory space, and what memory space is preferred by each execution space. That in principle allows us to support things like NVRAM, DRAM, you know, on-package memory on the CPU, on-package memory on the GPU, scratch memory, etc., etc. Can we go on? So every view stores its data in a memory space which is set at compile time. So the view type includes at compile time as a type safety mechanism where the data is stored. That is important because that includes the information where it's supposed to be accessible. And how you do specify that is you essentially hand that as another parameter there. Yeah, click on. There's a number of these, there's host space, CUDA space, there's CUDA UVM space, CUDA host pin space, and whatnot. Now, generally, when you don't specify that, right? First of all, you can actually, let me get back to this. You can actually use an execution space as an argument there. And if you do that, what happens is that the view will use the default memory space of that execution space. The benefit of that is you can, for example, template some type of thing, on just an execution space, and then use that both to allocate your data to get it automatically in the preferred, thing for it, as well as use it for like the execution policies. If you click one further, if you do not provide a space, then what we do is we use the default memory space of the default execution space, so that if you allocate a view, without specifying a memory space, and you execute without specifying an execution space, that actually works, right? There's also the opportunity, we have a couple of like defaulted aliases. There is a Kokkos default execution space and the Kokkos default host execution space. So in many cases where you just have like one type of accelerator and some kind of host thing, just using those two will be enough to distinguish where to execute. And that then would work for the HIP backend, for the CUDA backend, for the SYCL backend, and for the pure like CPU OpenMP backend. Can we go on? So what I said about this defaulted here, right, is that essentially view double star, right, would be equivalent to view double star default execution space colon memory space, right? It's also equivalent to view double star just default execution space, right? Because that's then implied. You could leave that memory space off there. Okay. So now let's think about that, right? Say we have something in host space or default host execution space, right? What you actually have as a view is you have two things, right? You have the metadata, which is the struct, the view struct, and you have the data it points to via its pointer, right? And when you create that guy in just like your normal process, both of these things live on the CPU, right? The object host view is just in registers or whatever, right? It's just a stack variable on the host thread, and it points to host data. Okay, let's go on. Click. If you allocate something in CUDA space, right, or default execution space, if you happen to compile for CUDA, the metadata will still be on the host, right? Because view is created as a stack variable in your calling thread. But it will point to data living in the GPU, which means you cannot access it right after there, right? You can't just access it with a host process thread. Okay, next. Now, let's think about that for a second. Say I allocate something in CUDA space, right? And I then read that stuff in from a file, right? In just a serial loop in your host thread. And then you run a Perl reduce, or Perl 4, whatever, where you access this array. Where's the problem? Can you click? The problem is that that first thing will fail, right? You access it, you're trying to write to something in your host thread, which actually is allocated in CUDA space. So that will not work. Now, you could change, click, this thing to host space, right? Now this first thing will work, but the second one will fail, right? It will give you an illegal access. The funny thing about this is that it actually potentially will give you an illegal access, long after your kernel failed, because the kernel might be running asynchronous, and so you only get asynchronous errors. Okay, so what's the solution here? There's a couple of approaches. One approach is we use unified memory, right? Unified memory is something which CUDA has, which HIP doesn't have that right now, but OpenMP introduced that recently as and SYCL has that as well. And what that allows you to do is this is essentially a memory space which is accessible from both the host and the device, and which uses some kind of hardware mechanism underneath to move data where it needs to be. There's a couple other versions, there's, for example, host pin space, which exists for both HIP and CUDA.
that memory is also accessible from both sides, but it is actually pinned to the host DRAM, right? So if you access it from the GPU, you actually go by a PCI Express bus all the time. It still has its uses, in particular in communication patterns, and we go into that there's a whole sub-lecture online on Kokkos and MPI, and we'll talk about how host pinned memory is useful for that. But the main way I want to introduce is mirroring, and we're going to talk that in a bit. Next slide. So what mirrors are is they are essentially equivalent arrays residing in a possibly different memory space from, its originator. Click. So how that works is the most common thing is to just create host mirrors. And what you do is you have this view type, you create a view, and then you create its host mirror. And you can do that via the create mirror view function. Okay. And what that gives you is now you have two views now, right? The view and its host mirror. And one of them points to GPU data and one of them points to host data. And you can move data between these two via the deep copy function. Okay, can we click? So how does that work as of the whole mirroring pattern? As said, you create first the originator view, and usually that's your device view. Then you create a host view using the host mirror, type def, which is part of like the view type, and you use it via the create mirror view. Actually, nowadays, a lot of people, what we do is we just do like, in particular, if you just create it temporarily, which may or may not be a good idea, you can also just do it via auto, right? What you often want to do is you populate that host view on the host, from a file and some kind of setup phase or whatever. And then you deep copy the data to the device side. Then you, run your kernel, you work on that view, and if need be, you copy the data back again. Okay. Now, one of the questions is what happens if you actually just run on the host, right? If you just compile for a normal CPU system, right? Do you actually get a copy? You don't want a copy, right? Why would you waste your time with creating an extra copy, use more memory, and then do all these deep copies? And that's where create mirror view comes in. Create mirror view actually, this view appendix where essentially indicates that it may not necessarily create a new allocation. If the host process can already access the view, it will just return that view. So host view and view would alias each other. It will only allocate if the host process cannot access the original view. There's another function, create mirror, which always allocates data. There might be algorithmic reasons why even if you're just running on a single CPU, a single memory space thing, you need to do that. And so create mirror can do that. There was a question here. Since these memory spaces are wholly different types, it seems like it would be complicated to take the same code base and have equivalent builds for CPU only, CPU plus NVIDIA GPU, CPU plus AMD GPU, and so on. Yes and no, right? As I said earlier, if you are just concerned about like CPU platforms and you just do the normal stuff without any special memory semantics where you just need device memory and host memory, right? This kind of semantic, right, where the host mirrors are actually just aliases, right, means that if you use default execution space and its memory space and default host execution space and its memory space, that will just work, right? That will work for, if you just rely on that and that's all you need, that will work with HIP, that will work with CUDA, that will work with CPU OpenMP, that will work with GPU OpenMP, that will work with SYGL, right? The problem is if you need more special semantics, like for example, you actually want explicitly host pinned memory, right? Or you want page migrating memory or something. These things are not necessarily available on each platform. For example, on current AMD HIP, you do not have page migrating memory, right? There is no semantic equivalent of like the CUDA UVM space. The way we handle that in our bigger applications when we need to do that is we have somewhere a single central header file, and that header file type defs all our view types. So we actually don't write like Kokkos view ***, you know, UVM space or whatever. We write, you know, forces _type, you know, positions _type and stuff like that. And so if you do these type defs, you know, in a single header file somewhere, that means you can change your view types and what memory they end up in, you know, just in that one location. And basically then in that single header file, you do an if defing depending on what you compile for. You know, sure, it's still, you know, a few lines of different code per backend, but at least it's fairly, you know, unified. LAMS, for example, does that. If you go into LAMS, it has somewhere a file in its source Kokkos directory, which is called, I think, Kokkos _types or something like that. And that's where it defines all these types. Okay, I hope that answers that question and seems like a reasonable approach. Again, right, the baseline is if you just use default execution space and default host execution space and its internal type defs for memory spaces, you don't need to do any changes between platforms. But if you need that other stuff, then do it in a central header file. Okay, next slide. So I think we're gonna do that. We're gonna have time to do that exercise when later. Basically, in this exercise, we're gonna explicitly use, you know, the host mirrors and the deep copies for the views. Okay, so to summarize that, data is stored in views in Kokkos programs, which are behaving like pointers. They are multidimensional arrays residing in memory spaces. This abstracts away platform-dependent allocations, as well as deallocation and the access. If you have heterogeneous nodes, we have one or more memory spaces, and you use mirror to create essentially copies to go back and forth between these things. Heterogeneous nodes also have potentially one or more execution spaces, and you can control where parallel code runs by template parameters on the execution policies. Okay, let's go on. Any other questions on this? If not, I think we are actually basically at our break, right? So I would just break now and then go after the break into this thing. Is that right?
I cannot check the agenda. Roy, are you here?
Yes. Hold on. I have too many windows open at the moment. That sounds plausible.
I think we had 1.5 hours and then like just a 15-minute break or so.
There it is. It's staring me in the face. We're scheduled for our break at 11. Yes, we're right there. So 15-minute break.